All right, here's another problem. And I always do this problem because there's all sorts of ways to make mistakes on this problem if you're not super, super careful. And I like to point that out so you don't make mistakes. Okay. A 2 kilogram solid sphere travels around a ½ meter radius circle with an angular speed of 12 radians per second. The circle is parallel to the xy plane, which is the floor, and is centered on the z-axis 0.75 meters from the origin. So it's kind of like this. So just 0.75, just pretend it's here, right? So the center of the circle is here, and so there's a circle like this, right? So this 2 kilogram sphere is going in a circle like that. All right. Find the magnitude of the angular momentum about the origin. Okay, now the origin is the floor, right? Right here, where the meter stick touches the floor. That's the origin. And so we have this sphere going like this. And we want to find the angular momentum relative to this origin. Okay, so that's what we have to do. All right, now, in my opinion, it's a good idea to draw the picture. This is a pretty bad picture, but I hope you understand what's going on. All right, so this is the floor. This is 0.75 meters, and then this is this circle, right? Okay, and let's say it's going like this. It doesn't say, so who cares? It doesn't matter. Just choose whatever you want. You can choose this or this. Doesn't matter, because we want the magnitude. Okay, so if it's like this, at this point it's moving away, so that's why I put this, right? The momentum P is moving away, and then here it's moving toward. So that's why I do it like that, toward. Okay? All right, so let's do it. Okay, now, you notice that the question is, find the magnitude of the angular momentum around the origin, or relative to the origin. So this is not one of these I omega things, you know. I mean, here you have to use the challenging definition. So the vector L equals R cross P, right? L equals R cross P. Vector cross product. And that's why I labeled, you know, so here's the R, agree? So this is the position vector R. It goes from the origin to the particle. I just drew it here. I mean, you know. And then there's P, right? Remember, P is mv. So P is mv this way, mv that way. Okay. Now that's the equation, but we want the magnitude. So what's the magnitude? So the magnitude of L is magnitude of R cross P, which is RP sine theta. Where theta, you got to be careful now. Remember, theta is the angle between this vector and this vector. We'll worry about it in a minute, don't worry. And I guess I could write that is, what's P? You know, P is mv. So I could say RmV sine theta. All right, now, here's the challenge. Here's R, right? Well, what R? Is it this R? Is it the magnitude of this R? Is it the magnitude of that R? And so you have to be able to figure that out, okay? Oh, boy. All right? Well, let's see. Also, you know, what's V? I mean, look at it. They gave us the angular speed. So, you know, V is R omega. Oh my gosh. Which R? So what's that R and what's that R? I mean, you got to be able to do that. Maybe we should subscript them, whatever you want to do. But look at it. You should be able to figure it out, though. From this definition, this is the position vector, right? So this R is the magnitude of this. This R, maybe I should say position vector, I don't know, position vector. This R is the radius of the circle. right? Because, V equals R omega, radius of the circle. So you got to keep your R straight. You just can't, you just can't be a robot and just use this 0.5 meters for this and for this. It's completely crazy, All right. So let's do this first. Doesn't really matter. So V equals R circle. So our circle is a half a meter. They told us that. And omega is 12 radians per second. So that's 6 meters, right? This is half a meter, sorry. 6 meters per second. Okay, so that's V, right? That's V. Now, let's get this R. Let's get this R, the position vector, okay? Well, how are we going to do that? Well, what kind of triangle is this? It's a right triangle, so this is just the hypotenuse, okay? So that R position vector is just square root of 0.5 meters squared plus 0.75 meters squared. I promise you do that, you get 0.9 meters. All right. Okay, so let's see. We have the R position vector, 0.9 meters. We know the mass. We get this V, right there. What's theta? Now that is tough for many students. So let me see if I can sort of demonstrate it. Okay, so that's the origin. The particle, or the 2 kilogram sphere, is going like this. So let's look at right here. Okay, origin. So here's the particle going in a circle, right? So here's a position vector, and the momentum vector is away from us, right? So what's the angle between this and this? What is it? It's 90. Let's do here. Okay, so circle, position vector, the thing's coming towards us. What's the angle between the position vector R and the momentum vector? It's 90, which is nice because, why is it nice? Because what's the sine of 90? Right, so theta is 90, and sine of 90 is 1. So that's nice. Okay, so let's just finish up the problem then. All right, so the magnitude, so therefore the magnitude of L, okay, R position vector, 0.9 meters. And then M is 2 kilograms. V is 6 meters per second. And sine of 90 is 1, so I waste time to write that. So 10.8 Newton meters. Why is it Newton meters? Well, just figure it out, right? What's momentum? Momentum is mv, so it's kilograms times meters per second. What's r? Another meter. So it's kilograms times meters squared per second. What's a Newton? A Newton is a kilogram times meters per second. So I have a Newton meter. Ta-da! Okay, this is a tough problem for most people. Because why? Well, because there's 2 r's. There's the radius of the circle, and there's a position vector, this guy, that points from the origin to the particle. So if you're not careful, you can get those r's mixed up. And the second challenging thing is the angle between this position vector and the momentum vector. So study that. Make sure you understand it. It's a good problem. I think I kind of like to say, not trying to be insulting or anything, this problem separates the robots from the thinkers. And so you want to be a thinker. Okay. Let's see. Okay, let's do this one. So read it, please. Okay, a 40 kilogram, 5 meter long beam is supported but not attached to the two posts shown in the figure. A 20 kilogram boy starts walking along the beam. How close can he get to the right end without the beam falling over? All right. Okay, what's the object? Hopefully you agree, the beam, right? The beam is the object. Okay, what are the forces acting on the beam? Well, there's a normal force here, normal force here, weight of the, okay, we got to be really careful here. So here they use uppercase B for boy, lowercase b for beam. I think I just use P for person, but whatever, right? So look at this one. The weight of the beam is at the center mass, right? It's a 5 meter long beam, so the center mass is 2.5. And then the child's weight is right there. And what we're trying to figure out is this x, right? This x. Okay, now, when the boy gets to a point where the beam starts to tip, what is this normal force? It's 0, right? When the beam tips, when it starts to tip, there's no contact here. So F1 would be 0. All right? So that's kind of nice, okay? So when the beam tips, F1 is 0. Man, this is getting sad. All right, so F1 is 0 at that tipping point. And that's what we care about, right? We want to know x at the tipping point, when it just starts to tip. So at that point, F1 is 0. Okay, now we have a choice. This is a torque problem, you have to admit. I hope you recognize that because, the beam is rotating. Okay, where do you want to put your axis? Your rotation axis. It's totally arbitrary. But remember, the place where you want to put it somewhere so you get rid of as many torques as possible. So where do you want to put the pivot? It's up to you. Well, what do you know? You know the weight of the boy, right? You know the weight of the beam. Do you know F2? No, I don't know F2. I guess I could figure it out, but I don't know it right now. So hey, let's just be lazy. What do you say? Let's put the pivot right there. Okay, then we don't have to deal with F2. Might as well, all right? So let's put, all right, so F1 is 0, and F2 is the pivot point. And that's going to make the torque equation really, really nice, right? Okay, so what we want is the sum of the torques to be 0, right? All right, so sum of the torques, 0. Okay. I guess I'll just follow what Randy Knight does. I'll use uppercase B for boy, whatever. All right, so here's the pivot. Looking at this only, nothing else, just this and the pivot. This is going to make it go clockwise. So what's the sign of the torque? Negative. So we have negative, so it equals negative mass boy, G, right? There's the weight, mg. And then what's the lever arm? Well, here's the force line. Here's the pivot. So this is the lever arm, right? It's just x. X. All right. Okay, so we already said that's 0. Our pivot is here, so we don't care about that. What's the only other torque? Just the weight of the beam. All right, again, forget everything else except this force and the pivot. Right? Forget everything. So this is going to make the thing rotate counterclockwise. So it's a positive torque. So we have plus mass beam G. And what's the distance? Well, this is given to be 3 meters. This is 2.5, so, right? This is the lever arm, right? Here's a force line, lever arm, 0.5 meter. And again, that has to equal 0, our favorite number, okay? All right, so this is equal to 0. So I can just put this on the other side and have that, right? And have that. So solve for x. get rid of the g, divide by the mass of the boy. Okay, and mass of the beam, 40 kilograms. I'll just do it over here. 40 kilograms times a half meter. Mass of the boy is, what, 20 kilograms? Small. All right, oops, sorry. Okay, 2 times a half is 1. So 1. 1 meter. There you go. So that's just a nice torque example. Okay, this is a really nice little video. I'm not going to show it now. So please take the time and click on this. It's just super useful. Minute physics. So they explain something super briefly, but they do a really, really good job on it. So make sure you look at that. Okay, what did we learn? Chapter 12. We extended the particle model to the rigid body model. So we have to talk about center of masses, and we had to include rotations, and we figured out rotational inertias, and rotational version of force is torque, rotational version of angular momentum is angular momentum, and all these kinds of things. To understand the equilibrium of an extended object, okay, we already knew this, but now we had to add this, right, some of the torques. To understand rotation about a fixed axis, so I'm just standing with a wheel that's rotating. To understand rolling motion, so now the wheel is moving along as it rotates. So two types of kinetic energy, right? To introduce the vector description of rotational motion and angular momentum. So a lot of equations in this chapter. So, we learned this a long time ago. You better know that, right? So you start off with this, which you know. Take the derivative, you get that. Take the derivative of that, you get that. And then you need to know the rotational kinematic equations. And again, it's nothing new. Just use the regular kinematic equations, just substitute for rotational, Okay, the x center mass for point particles. And here's for a rigid object. And then in order to do this integral, you have to get rid of the dm. You get rid of the dm by saying that we have uniform density. So for a one-dimensional object, the density is the mass divided by the distance. So the small mass divided by the small distance equals the total mass over the total distance, and so forth and so on. And we did a lot of examples on that. Then torque, this is the magnitude, the force times the lever arm, or the r times the tangential force. There's the vector r cross f. And remember that r cross f is equal to negative f cross r. So you don't want to switch the order of these vectors here. Equilibrium, we already talked about that. Okay, this is F equals ma. Torque equals I alpha, right? Torque is rotational force. I is rotational mass. Alpha, rotational acceleration. Okay, I is this messy thing, sum of mr squared, or integral r squared dm. And remember, for common shapes, the I is found on that table, which I will include on the exams. Rolling motion, you have translational motion plus rotational motion. So translational, half mv squared, rotational, half I omega squared, which totally makes sense, right? Because I is like the m, omega is like the v. Okay, now the complicated thing was L. L equals r cross p. So another example of this cross product, you have to know how to do that. This is only if you have a symmetrical object rotating about its center of mass, which we have a lot, so we use this a lot, L equals I omega. And then, remember Newton, when he wrote his second law of motion, he did not say this, all right? It's true, but he didn't write it that way. He said that the force equals dp dt, all right? And so the angular version of that is this. The angular version of force is torque. And then the angular version of p is L, so we get dl dt. So that's super important, right? It's in the second law of motion, you know. So there you go. So this is a long, challenging chapter. You know, we did that demonstration with the discs and the spheres and all that, you know, which one came in first when it went down the incline. And we used conservation of energy to figure that out. Make sure you can do that. You're going to probably need it, well, you're going to need it on a task, and you're going to need it in lab. And it's a great problem because you use so many concepts that we've learned throughout the semester, so make sure you can do that. And that's it. Thank you.